Hello everyone and welcome to All Things Air Quality. In this video we will cover how to determine stack moisture content using USEPA Method 4. This is typically applicable to when you're using USEPA Method 5 or USEPA Method 17, as well as many other of the isokinetic USEPA methods. The basic principles of this method is that you will be sampling isokinetically. As you can see here from the strain, you have the probe where you'll be sampling the gas in isokinetically using either in-stack or out-of-stack filtration. You have a condenser in which you will be condensing the moisture that's inside your gas, and then you have your metering system of your train. The standard for this method is to use a heated sample line. The reason for this is you do not want any condensation in your probe. You want to be able to take the gas, keep it above its dew point until you get it into your condenser. There are conditions under which you can do non-heated probes or even non-isokinetic sampling. The reason for isokinetic sampling is if you have any droplets or aerosol in your stack, you want to be able to capture a representative sample of those droplets using isokinetic sampling. But if you are under conditions where you're either above the boiling point of the water, so if you're above 100 degrees Celsius, the water won't be in droplet phase, so you will be okay unless you're dealing with oils or something like sulfuric acid mist. Then you don't have to go isokinetically, and you can use a non-heated line if your ambient conditions are above the dew point of your stack and there is no droplets in your gas phase, which means there will be no condensation in this line, even if you cool it down to ambient conditions, in which case you don't have to worry about using a heated probe. But the standard method is isokinetically sampling to capture the droplets accurately if you're below 100 degrees Celsius, and then also using a heated line, especially if you're above 100 degrees or if your moisture content is going to be above the dew point outside, because then you don't want that condensation in the line before your condenser. And then just a note, typically inside this condenser you will have your impingers that you've put in water, and you force out condensation of those impingers, and then lastly you have a little silica gel trap. That silica gel trap will capture the last bit of moisture that you do not condense out. But there is an option where you don't have to use the silica gel, in which case you can use the outlet temperature of your condenser. If you are able to cool down the gas enough so that it's saturated with water, you can then use that temperature to calculate how much water is not condensed. Using method 4, the key parameters that you need to be concerned with are the start and end DGM volumes, so your dry gas meter reading at the start and the end of a test, because you need that to know how much of a sample you took. And with that, you also need to record the DGM pressure and temperature, because the volume is temperature and pressure dependent. Then you need to record the volumes of water in your impinger, so your first and second impinger. You start with 100 milliliters in each, and then you just record how much in them afterwards. And then lastly, you will record the mass of your silica gel before and after the test, because that difference in mass will be the mass of water that is absorbed by your silica gel. As mentioned, there is a method of not using silica gel where you can use the outlet temperature of a condenser. In any case, this should be recorded to confirm that your condenser is efficient enough. You want to be below at least 20 degrees at your condenser outlet. I always say aim for 10. That is to ensure that you force out condensation from the stack so that you can get an accurate reading. Just a little note here on the sampling train. The train I've shown in the previous slides, that was a USEPA train. Now, the European train, primary difference is the dry gas meter position. It's just going to be before the pump in this European trains, which is my preferred train, because then you don't have to worry about pump leaks, because you do all your volume recordings prior to the pump. The principle of this calculation, we want to know the water fraction in the stack. That is the aim, that is the parameter that we want to measure using our sampling. And the water fraction in our stack is going to be equal to the water fraction in our sample, because we're going to draw it isokinetically with a heated line. And that can be broken down to, again, as the total water that we sampled divided by the total volume of sample that we drew from the stack. What that means is the total gas that we sample. So here we draw gas out of a stack, we force it through a condenser. We're going to remove water from that gas stream in our condenser. It's going to stay behind in our impingers and our silica gel. We're going to take our gas, it's going to run through the metering unit, our dry gas meter, and through the pump and out our train. The water fraction in the stack is equal to the water fraction of sample, which is equal to the water we removed here divided by the volume that we've sampled, which is not just the volume of a dry gas meter, but we also have to consider the volume that we've actually removed from our sample here in the form of the liquid. And that is where this calculation can get a little bit complicated if you are not that familiar with gas properties. The total volume that we sampled is the volume that we record here in our dry gas meter, which is gas phase, a liquid, water that we condense out, and some water that we trap on absorbent. The gas volume that we sampled is, if you take this water that's in the silica gel and in the impingers and you convert that back to the gas phase, how much was it over here? Because that's the total that we sampled. And this calculation deals with that. Our first term here, the volume of gas sampled that we record here with our dry gas meter. That's fairly simple. This term is the volume of our dry gas meter. You'll see that we work at normal conditions because these things are based on a mass balance, and gas volume can only be used in the same sense as a mass balance if you're working at the same conditions. That's why we're going to work out our normal conditions. So we take the volume of our dry gas meter, the final minus the initial of a test. That's our change. That's how much gas we sampled at our dry gas meter's pressure, as the pressure gauge will record, and the temperature of our dry gas meter to record with our thermocouple. And we normalize that dry gas meter volume using this term from the ideal gas law. So it's our pressure that we recorded divided by our normal pressure times the normal temperature divided by our dry gas meter temperature. Important note here, we are working with absolute temperatures and pressures. So if you're in metric units, use Kelvin. Do not try to use your degrees Celsius because it's ideal gas law based. It will be wrong. You have to use Kelvin and you have to use absolute pressure. So that's the first term. That is the volume that we sampled in the gas phase that went through our dry gas meter. The rest of this video is going to deal with this term, the volume that we removed in the condenser. Now let's get into that. Okay, so that term, the volume removed in the gas phase, just a reminder, it fits into our main equation that we want to use here, which is the volume of water we sampled divided by the total gas that we sampled. Now the volume that we removed using our condenser consists of two parts. First, it's the volume that we condensed in our impingers plus the volume that is trapped in our silica gel. I'm going to start off with the silica gel because that's slightly easier to calculate. So for our silica gel, we want to know the volume in the gas phase, but what we've measured the mass change of that silica, which represents the amount of grams of water that was absorbed onto the silica. Now, to convert that grams of water to gas, we use the density of water in the gas phase at the normal conditions that we are working with. So you can use that density to convert the mass into a volume. So you typically take your mass, say you have 10 grams, you divide it by your gas density of, say, 1,000 grams per cubic meter. You can get your volume of water in the gas phase removed in the silica gel. The second term is the volume removed from the liquid, the volume that we've condensed. So volume we condense is in the liquid phase. Remember, we want to be working in the gas phase. So again, we go back to mass balance, mass principles. We can say that the mass of the condensed gas is equal to the mass in the liquid phase because mass is conserved. And that mass is equal to the volume of water we have condensed. So if we have, say we started with 200 milliliters of water and we finished with 210 milliliters of water, we had 10 milliliters of water condensing. If you take that 10 milliliters of water and you multiply it by the density of water in the liquid phase, you will get the mass of the water that you condensed. Now we have the mass of our water in the condensed phase. We want the volume of that water in the gas phase. To convert that mass into a gas, you divide by the density of the water in the gas phase, again at the normal conditions we want to work with. And that will give you the volume of water. Just a note here that the water density in the gas phase is a function of temperature and pressure. We've also used it up here. And finally, the total water volume you removed is the sum of the two terms. It's this term over here, the volume removed in the condenser, plus the volume removed in our silica gel. You can just add it all together. But just a little tip or a note, I calculate these two parts separately. The volume of water removed in the silica gel and the volume of water removed in the pinches, just so that I can check myself. Finally, just a little comment on how you can actually calculate for water without the silica. Same principle applies. The water fraction in the stack or in the sample is equal to the total water that we sampled divided by the total volume we sampled. Now, if you do not use silica, we cannot assume here that there is no water leaving the condenser. So what you have then is the total water that you sampled is this water that you condense out, plus the water that actually goes to your dry gas meter, divided by the total gas that you sampled, which is the water that you removed in your condenser, calculated as in the previous slides, and the volume of the gas going through your dry gas meter and pump. Now, the water here leaving the condenser can be calculated if you know the outlet temperature of your condenser. You make the assumption that the outlet is at saturated conditions, and then you can use that temperature to calculate the vapor pressure of water at saturated conditions, and you can use that to get the volume of water leaving your train here, typically using the Antoine equation. It's slightly more complicated. It is very accurate because you do not assume an efficiency of silica gel or anything like that, and I will do a different video covering that calculation specifically. Right, thank you very much. The next video will show an example calculation using principles and equations in this video.